All right, welcome everyone. This is the OpenCL session here at GDC 2015. It's good to see you all here. And we're going to give you a brain dump on everything new to do with OpenCL and give you some insights into the new developments that we've been announcing here this week. We're actually going to be covering 3 standards, OpenCL itself, but related standards, SPIR and SYCL. And if you don't know what that means, you will very soon. So how many people here have never heard of Khronos before? Do you guys know who Khronos is? Oh, shut up. So Khronos we're an open standards organization. We're open to any company to join. We have about 120 companies, everyone from Apple and Intel all the way down to individual developers. We define open standard APIs that let developers get to call hardware acceleration, graphics acceleration, vision processing, sensor processing. And we have about 12 active APIs. They include things like OpenGL, OpenGLES, OpenCL that are used by literally billions of devices around the world. But today we're here to talk about OpenCL. OpenCL is also pretty widely deployed in the industry now. So OpenCL is for compute acceleration, OpenGL for graphics, OpenCL for compute. And a number of different types of API are now using OpenCL on both mobile and desktop platforms, imaging, vision, compute, simulation applications from companies like Adobe, Apple, Sony, Dassault in the CAD space, Houdini. Mathematica has an OpenCL backend. Anywhere where people want to get to compute acceleration, OpenCL is a great way of doing that. There's also a bunch of open source projects. We've actually counted over 2,000 open source projects out there in open source land using OpenCL. And benchmarks, and we're going to get an update from one of the leading benchmarks here today as well. But it's not just desktop, it's mobile, because mobile phones are increasingly becoming processor clusters. We have multiple CPUs, 8 is not uncommon, quite sophisticated GPUs, DSPs, hardware blocks for camera and vision processing. OpenCL is a heterogeneous programming framework that lets a developer access the power of all of those processors from one consistent API and language. And we have a number of mobile developers, kind of the who's who of mobile GPUs, are now shipping OpenCL on mobile devices. And an interesting trend that we're finding in the industry, there are 2 ways that folks are using OpenCL. One is the programmers that are programming directly to OpenCL and using all of the language and API features that we're going to be updating you on in just a second. But there's also the high-level languages and frameworks that are emitting code and wanting to access compute backends, parallel computation, hardware runtimes. And OpenCL has become really the de facto choice for people wanting to run emitted code on parallel hardware. We've actually counted now over 200 different languages and frameworks, things like Halide for image processing, C++ AMP for high-level parallel programming, Java bindings, JavaScript bindings. It's people using OpenCL and OpenCL-C as a compiler target. But we think some of the announcements we're making here this week are going to accelerate and even more facilitate this trend as OpenCL as a backend. So, for those of you that might be coming across OpenCL for the first time, what is it? Well, it's a set of 2 APIs and a parallel language, or languages. The idea is that you use one API to find out what's in the system. You write kernels in the kernel language, and then you use the runtime API to compile and distribute the kernels for execution and gather back the results. Now, we have a number of updates here at GDC. There are updates on the languages that we can use to program the kernels. There are updates to how we can load those kernels into the hardware. And there are updates on the APIs that we can use to control that execution. So, without further ado, what is this announcement? It's OpenCL 2.1. We've announced and released the spec publicly here on Tuesday. So it's released as a provisional specification, so we haven't finalized it yet. We think it's good, but we want your feedback as a developer community before we bake the final version. So we're genuinely requesting feedback from the community of developers that want to use OpenCL. So what are the headline features in this new version, OpenCL 2.1? The big ticket item is we now have C++ as a kernel language. This is by far the largest request we've got from the developer community. It's a subset based on C++ 14. It's the static subset of C++ 14. We still have OpenCL C. Nothing has disappeared, so all your investment in current code will continue to run. But now you have the choice of using C++. We have Lee here from Qualcomm who's going to give us a lot more details on that. The other big announcement, and in some ways it's almost more significant, I think, is that we now support SPIR-V as an intermediate representation. Now, we'll explain more what that means, but at a high level, SPIR has been the intermediate representation for a while for bringing in code that's not in source form. We have a new version called SPIR-V that now supports C++ for OpenCL 2.1. It's also being used by Vulkan, and so a really significant advance for the ecosystem. We get asked a lot, does it mean I need to buy new hardware? The answer is no. This is a software update, so any hardware that runs OpenCL 2.0 will run OpenCL. Any hardware that runs 2.0 will run 2.1. And you can see the timeline is here at the bottom. We're on like an 18-month or 20 to 24-month tick, and we've released a provisional spec after 16 months. So we'll close the spec, and we'll be roughly on that tick too. So we're updating the standard to meet the needs of the developer community. So we have Ron here from Intel who's going to give us a lot more detail about SPIR. But I just wanted to kind of just show at the big picture from 50,000 feet how this kind of fits together before Ron dives into those details. SPIR-V. It's called SPIR-V because SPIR grew up through OpenCL, but now it's also used by Vulkan. So kind of the two things coming together. It's the industry's first cross-API, cross-vendor intermediate language that includes parallel computation and graphics. So we can natively represent Vulkan and OpenCL source languages, both C and C++. So we've gone beyond what's available in LLVM. And it's such a powerful place to split the compile chain. The front ends that are the domain of the language experts, domain-specific frameworks being put together that want to emit intermediate code. We're allowing parallel innovation with the hardware community. The hardware guys ingest the SPIR-V and run it and accelerate it beautifully. That's the idea. So now we have the software guys innovating in languages and frameworks independently from the hardware guys innovating on hardware architectures. And we also think that this brings a real opportunity for the tools vendor community to actually develop and ship tools for software in SPIR form. And I think it is pretty big news that Vulkan and OpenCL now have both converged on using the same IR. It's a stepping stone in converging languages for graphics and parallel processing. So some people get confused on the various terminology. So this is kind of a table that explains what all the versions mean. SPIR is the umbrella term for anything to do with any of these versions. SPIR 1.2 and SPIR 2.0 shipped with OpenCL 1.2 and OpenCL 2.0. It's SPIR-V that is a superset in terms of functionality, but doesn't use LLVM anymore. It has native support for compute and graphics constructs, supports all the languages that were supported before, plus OpenCL C++ and GLSL for Vulkan. And it's in the core. Ingestion of SPIR-V is in the core of both Vulkan and OpenCL 2.1. So the way it works, if you have an OpenCL 2.1, you still have the traditional way of taking OpenCL C and having the runtime, having the driver ingest it directly in source form and compiling and running it. But now we have SPIR-V. So you can have a SPIR generator that takes OpenCL C and converts it to SPIR for ingestion that way. But this means we can have a diversity of new languages that also target SPIR-V, and of course OpenCL C++, which is a part of the specification of OpenCL 2.1 through SPIR-V being ingested into the runtime. So that's the high-level overview. I'm going to hand it over now to the folks who can give us more detail. But just the last thing before I do that, we're very serious. We actually want feedback. Are we headed in the right direction? Are we focusing on the right things? We've opened up the feedback forums on the Khronos website on Tuesday. We have one for OpenCL and one for Vulkan, one for SPIR-V. If you have any thoughts and you'd like the working group to know about them, please do post your comments there. So, and we're going to have time for questions at the end of the session, but you have a question, go ahead.
Just an idle question. I'm curious why Vulkan doesn't have a suffix like every other API does.
A suffix, like OpenCL, yes, do you mean?
Yeah, why isn't it Vulkan 1?
Oh, well, it is Vulkan 1. But it's 1, so we don't need to say it. But you're quite correct. When the finals, we don't have a specification yet, so we're doing a reveal of technical direction. So that's why we're calling it Vulkan. But you're quite correct. When the specification ships, it will indeed be Vulkan 1.0. Yeah. Yes, go ahead.
Is NVIDIA going to play along there?
With Vulkan or SPIR-V? Yeah, no, we're not sharing today, but yes, NVIDIA supports OpenCL. We are shipping OpenCL, as you know, 1.1, but we're going to be upgrading that pretty soon. Watch this space.
Second, if you mind, second question.
Yeah.
Are you guys planning on maybe in the future requiring any form of like performance counters in those specs, like compute side, for example? Because CUDA is fairly easy.
Yes. That's a good question. Actually, Vulkan is actually innovating on that in quite an interesting way, and that's a potential convergence point with OpenCL. We don't have any plans in place to do that, but given that Vulkan is innovating here, it's something that might go through. What Vulkan is doing is you have a loader, and you can load just the driver, or you can choose to load the driver plus debug and profiling tools and verification tools as a layer. And because in a production environment, you don't need to load any of those debug layers. You can just go straight to the driver, and you don't get any error checking overhead if you're running trusted code. But you can load the layers whilst you're in the development environment. So that's kind of an interesting way of enabling a good ecosystem of tools that can be quite powerful, but not overloading the driver if you're in a production delivery environment.
But that layer is only for like API level right now. Is that right?
Currently it's for API level. That's right. Currently it's for API level. Yeah.
Right. What I meant is like things like different like pipeline utilization counters where you use.
The Vulkan API does actually have profiling counters that are standardized for the first time across multiple GPU vendors. So it is for the first time going to be possible to have cross-vendor profiling and debug tools. And the layering architecture of Vulkan is actually quite extensible. So there's we just started on that innovation path.
Thank you, Neil. So yeah, I'm going to cover the API and the C++ kernel language, and we'll start with the API. So for OpenCL 2.1, as Neil said, it's only a software update. We're not requiring any new hardware features. And so what we've done is we've made a relatively small number of changes to the API, but a couple of the things we've added are quite big features. And now the biggest thing, as Neil hinted at, is the standardized way to consume the SPIR-V intermediate language. And in fact, this is to be the primary way to consume the C++ kernel language as well, which is the second one of the big features. The other thing that we've done is we brought subgroups into the core specification. and subgroups exist to expose the hardware threading in a more portable way. And then we've made a few other relatively minor things on the topic of performance counters. We've added low latency timer queries so you can time the device code. And then we have some profiling and priority and throttle hints. Oh, and the other very minor feature is you're now allowed to enqueue zero-size dispatches. Seems an odd request, but it was a corner case that was missing. So in the OpenCL API, we have 3 ways to consume kernels now. We have consumption from source, which is OpenCL C. It is not currently required to be able to consume the C++ kernel language from source. And the reason for this is that it is it seems more of a portability problem to try and have C++ front end that is compatible from one vendor to another. So instead, the approach we're taking is that you have a compiler library, either offline or an online one linked into your application that generates SPIR-V, and then that is consumed in a very portable and standardized way. So this IL is then a well-defined input for the platform. It will be this standardized SPIR-V, optionally with extensions. And so we have added specific API support for the needs of the IL. We've moved subgroup functionality into core, as I said. So this exposes the hardware threads, the wavefronts, the warps, whatever different vendors call them, with cross-lane operations, so that cross-lane operations on specific vector threads can be exposed independently of the ones we added in OpenCL 2 across a whole workgroup, which might require synchronization. And from the host API point of view, that's primarily a kernel language thing, we have queries for the ability for those subgroups to make forward progress relative to each other, which is a scheduling query, in effect, for the hardware scheduler. And for the mapping of the work items in work groups to the subgroups, because clearly you need to know exactly how your code's going to be running when you make all the get local ID queries and so on. One thing that we found when we were updating the C++ header was that copy constructors for kernel objects were very clumsy, because there was no way to actually copy the kernel object with all its state. Instead, you had to reconstruct it, and you had to reconstruct it to be a true copy. You'd have to reconstruct it with its arguments, but you didn't know what the arguments were. So we've added the ability to just copy the kernel object. It seems a simple thing. It's a minor change to the API, but it makes creating that sort of wrapper much easier. And we've added a low latency timer. So this is a pair of API calls. You can query a pair of the host and device timer at a point in time, and then you can query the device timer separately. So as your program's running, you can say query both timers at 2 points, so you can correlate them, and then your independent queries of the device timer can be higher latency because they have to go to a device and back. But you have a host timer to correlate them with now. So that's useful for doing certain types of profiling. And as an extension, we've added priority and throttle hints to queues. So you can tweak the priorities of queues. You can ensure that commands from a higher priority queue execute before those from a lower priority queue. And you can give levels of throttling so that a runtime can use frequency and voltage scaling or other techniques to throttle kernels if they don't need to run so quickly. So that was it for the API. They're relatively simple changes. We'll hear more about SPIR-V itself later, which is the really big change that's consumed. And now I'm just going to summarize what we've done for the C++ kernel language. So this is a static subset of C++ 14. It has the obvious things that you'd expect: classes, templates, operator overloading, so you can create reusable libraries. You can specialize libraries based on the type. You can pass objects in that specialize the operation that your function is going to perform, and so on. And so to make this familiar to C++ developers, this also means that we can incorporate a lot of the standard library features, like the standard C++ 11 atomics library, or at least a subset of it, some of the type traits, mathematical functions with standardized overloading, and so on. Obviously, given that this is a GPU and heterogeneous programming model, there are some restrictions. That's why we said static C++, dynamic cast operator, runtime type information, recursion, and a few other things are not allowed. And this is one thing that we'd be interested in feedback on, whether this set of restrictions is okay, or whether there are some things that we should be trying to work with. So just a simple example of a C++ kernel is exactly what you'd expect. We have kernels marked with a kernel keyword just like before, but we can template calls to this other function so that it's specialized on the type. That's obviously the most trivial example of doing this. But you can see that this add vectors function is templated on two different types, one the scalar float and one the vector float. We have the basic data types you'd expect, the scalar types, the vector types. We've tried to incorporate images more cleanly into the type system. So instead of being specialized types with type modifiers, we have templated types so that we can actually specify the color of the type of the pixels, and the access, whether it's read or read-write and so on, through templating, so that this is done in a consistent way with standard C++ code. It's less, there are fewer quirks in the language when you do this. And that applies to the pipe types as well. Pipes were added in OpenCL 2 as a way of something like a buffer, but that has FIFO semantics. And they are described similarly to images now. We've also added a program scope variety of pipes, and I have a slide later that shows what exactly that's for. And then the basic types for in-queue kernels. Now, one change we've made, partly because it's C++ and partly just for ease of use, we added the generic address space in OpenCL 2. And while OpenCL C specifies the global local constant address spaces, in many cases these are quite difficult to use, and they make it much more difficult to make code where you can reuse functions, for example. So as it's currently defined, OpenCL C++ 2.1 doesn't use these. The compiler would either have to infer them where it wants to get some optimizations, or it would be able to fall back to the generic address space. Now, for allocating data in local memory or in constant memory, which is still useful for many of the devices, we have classes, container classes, that allow you to manage that. So we have local pointer, we have a local array, which is roughly the same as the std array type from C++, and just a local wrapper, and similarly for constant. Now, one thing that this means is that you can actually regain a lot of the optimization you would have had from using the address space qualifiers, because you can always create a local array but pass a local pointer around. So you can carry a lot of that information through the compiler if you really want to, but in a very standard C++ way for standard C++ compilers. So it's cleaner, but we'd like feedback on what this is like, seems like for people. We have the standard library, which is based in part on the previous OpenCL standard library, but mapped to the more standard, well-known C++ construct. So where we have the C11 style atomics in OpenCL 2, we have C++ 11 style atomics with the atomic types that are templated in C++. Image functions that apply to the image object in a more object-oriented style. Pipe functions similarly. And the dynamic parallelism, or nested parallelism, now uses C++ lambda functions instead of the Clang block syntax to more to fit in with the style that people expect. So as an example of that, we in OpenCL 2 we added the feature where you can in-queue work from a kernel onto the same device using a device queue. And we did that using the block syntax. You can control execution order by creating dependencies between the kernels you launch, and within reason, you can do much of what you could do when enqueuing work from the host. The difference is that now we can do this using the more or less standard C++ Lambda functions, with the caveat that there is the function modifier that we have the same as for kernel functions that specifies that this is a device code. But otherwise, it's a standard Lambda function, and so this can be passed around. So there's there's very little quirky syntax here. We have device queues that you actually enqueue that work onto. You have the event types and ND range types and all the features you'd expect to be able to manage those device queues. And there's an example of that, a very simple example. Here we have a function. We have a Lambda type, a Lambda object that calls that function, and we can enqueue that Lambda, telling it to wait for the kernel to complete. It's the same as we could do in OpenCL 2. There are functionally no new features here, but we've mapped them into the C++ language to give a more familiar style to developers, which is what developers have been asking for. And then you can have more complicated examples where you actually add an event dependency between the kernels and enqueue them. But again, there is no new features. The final feature that is new here but derived from the pipes that we had before is compile time data flow. And this is really interesting for architectures that want to compile data flow offline, in particular FPGAs. So we've added a program pipe, which is a pipe object but allows you to declare it a program scope. It's a different type because this actually takes a size statically, whereas a standard pipe object is only available as a kernel parameter, so it's slightly different. And you can use these program pipes by writing into them in one kernel, reading from them in another, and you can see this dependence in the source code. So when the compiler views this entire C++ input, it can track the dependence graph. And so that way it can create hardware FIFOs, for example, or allocate buffers of the right size and just construct things so that everything's efficient. And so this might look something like this. So we have our two kernels that were being queued as we saw before. We have a program pipe, and then we have local pipes that actually give access to that program pipe and can be read from and written to. And so the graph between the kernels is completely static and visible to the compiler. And so this should allow some interesting optimizations, particularly on that sort of architecture. And that's it for the C++ kernel language. So I'm going to hand over now.
All right, guys, thank you very much. My name is Ron Krish. I work on Intel, specifically focused on compilers. And when we're talking about the SPIR-V and the SPIR family provisional spec that's been shown. Okay, well, getting the audio right, I'll just keep going. So SPIR is it's a standard portable intermediate representation. So basically, it's just a common binary format for our shaders and kernels. In the past, SPIR has just been for OpenCL, and we've done that in OpenCL 1.2 and OpenCL 2.0, expanding SPIR along the way to support all the features. But we're talking specifically about SPIR-V today, and that introduces support for not only OpenCL 2.1 and the C++ language. We also start introducing other APIs, such as Vulkan, that's being previewed this week. And with Vulkan, you also get GLSL support in addition to OpenCL-C and OpenCL C++. So, like we've kind of hinted at over the last half hour or so, SPIR is an intermediate language for the Khronos graphics and compute APIs. So it is a fully specified Khronos standard. We're not piggybacking on a specific version of LLVM anymore, so it's completely Khronos owned. And we can natively represent the graphics and compute languages. So kind of different from the old approach where we took something existing like LLVM and added hints to LLVM and extra metadata and side information such that we can represent our kernels and our graphics APIs. Now it is all the graphics and compute features are fully baked into the SPIR-V language. But we know that a lot of developers and compiler writers are using LLVM in their toolchain. So we also kept that in mind and made sure that we can go from SPIR-V to LLVM in a fairly easy and straightforward manner. So unlike previous versions of OpenCL, SPIR is now core in OpenCL 2.1. So no more extension. It's not an optional feature. So if you have 2.1, you are going to be able to use SPIR. And then if you're also developing for the Vulkan API, SPIR is core for Vulkan as well. So why you should use SPIR? Well, it's pretty cool. So a couple problems that developers have these days. If you're doing a fairly intensive app, you may have a lot of IP hidden into your OpenCL kernels. The same for your graphics kernels as well. And shipping plain text code to all of your customers isn't necessarily desirable for a lot of software developers. We also have some portability issues. Because you're compiling from source every time, you're kind of at the mercy of everybody's front-end compiler for this language. I mean, I bet you every one of us has compiled something on Visual Studio and had it compile fine, but you compile it on GCC, and you get warnings and errors everywhere. The same thing happens between different implementations of OpenCL. Since you're usually compiling OpenCL, or you were compiling OpenCL from source, you're going to pay a higher runtime cost to do these compilations. Right? I mean, every time you run your app, the runtime and the drivers are starting over from source. It just takes longer to compile your kernels. And because many vendors don't want to ship plain text source, they try to use APIs such as the create program with binary and offline compile a binary for every single OpenCL vendor there is out there. But that doesn't really work all that well, especially in cases where I compiled maybe I compiled an Intel binary, but I'm trying to run it on a newer piece of hardware than I compiled it for. It may not work. So SPIR tries to fix all these problems. So ideally, I can ship a single SPIR binary, and it's extracted enough from the high-level language to provide a lot of protection from shipping or sharing my algorithms. But it's low enough that any hardware vendor should be able to take this and compile it natively to their machine. So the other thing is it removes it removes being tied to an individual implementation or individual compiler's behavior. Right? All compilers have a little bit of DNA. If you like one front-end compiler better than the other, maybe it gives better warnings or better error messages, you can pick that one and compile your SPIR-V with that compiler and ship it across any vendor. It'll just work. Since you're not compiling from source anymore, top to bottom, you're going to have improved compile time and less API overhead. So you're just not sitting around waiting for your online compiler to do its thing anymore. Okay. So SPIR-V fully supports OpenCL C and C++, and everything you can do in OpenCL C and C++. So generic address space, atomics, images, pipes, all these things we love about this OpenCL programming language, they're native in SPIR-V. Right? We're not trying to shove support into an existing framework like we did with LLVM. These are all native types. You want an image in SPIR-V, we have an image type. You want a pipe in SPIR-V, we have a pipe type. There's no more describing my pipe as a void star pointer in the older versions of SPIR and then tacking along this extra information saying, no, that void star pointer is really a pipe. Treat it as a pipe. We don't have to do that anymore. So we also have support in Vulkan for SPIR-V. or we have SPIR-V support for Vulkan, including GLSL. So you get all the same benefits in Vulkan as you do with OpenCL. So faster compile times, you don't have to ship your plain text source. So this is a work in progress, so come back for the Vulkan talks to hear more about the Vulkan and SPIR-V. So for SPIR-V and OpenCL 2.1 implementers, we get the benefit that we don't have to ship a C++ front end. We just have to consume SPIR-V. Now, it's good for everyone. The engineering companies can take that developer time and work on making your kernels run faster because we don't have to be parsing languages anymore. And you don't have to deal with multiple vendors having slightly different implementations or different interpretations of the language specs. So good for everybody. So we're going to do a little overview of what SPIR-V actually looks like. So we've done a lot of work to try to make this language very easy to use, produce, consume, and understand. So SPIR-V is just a list of 32-bit words. So like any binary format, you have a little bit of header, but then after the header, it is a very easy to consume opcode followed by parameter list of instructions through the bottom. You should be able to parse this thing from top to bottom in one pass. You should be able to produce it from top to bottom in one pass. Very easy to understand and use. Now, once you get past the header information and describing the properties of your language in SPIR-V, you're going to have functions. A SPIR-V function contains a control flow graph of basic blocks, and then a basic block contains a list of instructions. These are all very familiar terms to anybody who's done language work or compiler work, and it's very easy to represent and understand. So like many languages, we can declare variables, we can load and store from them. And in SPIR-V, all intermediate results are represented in a form called single static assignment. This is a very nice property that many compilers and language parsers keep around. Now, if you look at the last three we just talked about, the control flow graph, load, store, intermediate results, these are also properties of that an LLVM module maintains in the LLVM intermediate representation. So again, we've done a lot of work to make sure that SPIR-V isn't tied to a specific version of LLVM anymore, but that converting from LLVM for an existing toolchain to SPIR-V should be a fairly painless task to do. So many, intermediate representations of other types require you to represent complex data types as individual registers or a collection of individual types. But we didn't do that in SPIR-V. So we have a hierarchical type system that's logically defined. So we can take a simple example. We have a struct with 3 fields. It has a 3x4 matrix of float 4s. We have a vector. We have a 6-component vec4 and a plain old integer sitting out there in our struct. And the way SPIR-V represents this fairly complex type is we start from the bottom up. We say, I have a single 32-bit float in my, start at the bottom at number 10 here. We have a 32-bit float. Then I'm going to take that 32-bit float and I'm going to build a 4-component vector out of my 32-bit float type. Now I have a vector type. Then I can say I can take a 3-column matrix type that is built off of the 4-component vector type. And the same thing for my array. Then at the end of the day, I can say my struct is a conglomerate of my matrix type, my array type, and my single singleton 32-bit integer type. So when you actually look at the code or the language instructions you omit for SPIR-V, you can easily put back together exactly what the high-level language looked like. So you should not lose any information about your types or the sizes of your types or like the possible bounds of the arrays even in these types. Okay. Now, SPIR-V is fairly easy to expand, and like this is a good example right here. So you can have multiple different addressing models in SPIR-V. You can say, my language is something like OpenCL and I want full use of pointers. Or you can say, my language is something closer to GLSL on the graphics side, and I don't have pointers. I have a more logical access where I'm accessing, texels. So I don't have to worry about the full side effects of having pointers in my language. So you can pick different addressing models and limit the feature set. SPIR-V is very easy to extend. Now, we're going to look at just one example here, but this is a feature in SPIR-V called the extended instructions. So all the typical instructions that you would want for your language is built into SPIR-V, but there's also a bunch of other instructions that are common to many APIs that just don't quite fit in a standard or a cross API language standard. So this example here says, hey, I'm going to import a bunch of instructions from the GLSL standard library. This is GLSL 4.5 we're going to load from. And then on this last line here, it says, hey, I want to execute extended instruction number 28. And if you want to know what extended instruction 28 is in GLSL, you check the GLSL spec for their standard library. It happens that this is square root, and you can execute square root from the GLSL standard library. Now, OpenCL has its own standard library, and it may just happen that OpenCL's extended instruction 28 is square root as well, but they are different. They are separately defined standard libraries, and each standard library may have different precision or accuracy requirements as well. So you can encode all of your debugging information into a SPIR-V binary as well. You want line numbers or file numbers or any other of your typical debugging information that can be encoded in SPIR-V. And before you ship your product, you can just strip all that information right out without changing any of the semantics or the behavior of your program. Cool. And so Khronos is working on an LLVM to SPIR-V conversion tool. So no commitments yet, watch this space, but it is in progress. So if you have an existing LLVM toolchain for a language of your choice, you should be able to use this to generate SPIR-V from your language. So now the general flow of using any of the SPIR APIs is you split your compile chain into two parts. The top half of this chart here is your offline part. So you take your program source and you run it through your SPIR generator. And today, you're going to take OpenCL C, OpenCL C++. You're going to likely run it through a slightly modified version of the Clang toolchain, and you're going to produce a SPIR-V binary. This can be done offline, so no paying runtime costs every time you run your application. No paying the power cost and the battery loss too if you're on a portable device for compiling your kernels. And then after you've done that, whenever you run your app, you're just going to give the SPIR-V binary to your OpenCL runtime, and it's going to do all the device-specific compilation and optimizations before finally running this. So we're all pretty excited. You see, every one of us have talked about SPIR-V a little bit. We're pretty excited. We are looking for feedback. So we have a spec available. We have a white paper that sums up all of the features of SPIR-V available as well. The white paper is very short. I recommend it if you're interested in reading this. And we're really interested if people can come up with something neat that they can do with SPIR-V. Do you have a language of your own that you want instead of C or C++? Hopefully this gives you the ability to do that in a fairly straightforward way. Since SPIR-V is completely open and easy to parse, you can maybe come up with some profiling tool or target it to a completely different backend that we didn't think of. So please take a look at this and provide feedback. We're very excited about this.
Hello everyone. Yeah, I'm Colin Riley. I'm a technical director at CodePlay, and today I'm just going to give you a little overview of SYCL, so the benefits, what it means for developers, and show you kind of the things that you can do in it. So SYCL is a royalty-free cross-platform programming layer based on C++. It builds on the concepts of portability and efficiency, and you can think of it as a higher level model on top of OpenCL. So it's single source C++, and it's without language extensions, which is a really big deal, and I'll come back to that later on in the talk. The single source development cycle allows for kind of functions that can be run both on host and device, and it allows developers to construct reusable templates for algorithms that are maybe based on old source code, and it's very easy to get that onto SYCL, and then use that for OpenCL acceleration. So the current state of play is that we've got the 1.2 provisional, and that spec was released last year. Aim is for ratification this year. You can see the provisional specification at that website. And the OpenCL forums have a SYCL thread for feedback that you can use to tell us what you think. So SYCL achieves an OpenCL ecosystem based on C++. And I noticed it's very very important to realize the differences, and that this is a single source C++ and it's not the kernel language that we've been speaking about previously. And it allows C++ developers to easily utilize OpenCL code and ship libraries, tools, and give them OpenCL support. And it also allows for implementations from many different sources, and allows developers to really utilize OpenCL and enable future innovation in their builds, in their source code, and in their products. So here's a kind of, it's quite big, but this is very simple. It's, imagine your user application code. It's quite a big application, and you'll be using libraries and templates from many different sources. You might have some that use other technologies that go down to a CPU or custom processor, and then you have template libraries that go between OpenCL and other technologies. Then you have ones based on SYCL, and those can go all the way down and target many different OpenCL devices, from CPU to GPUs all the way to FPGAs. So this is just a very simple example of some SYCL code. You have buffer objects, which are simply binding SYCL objects to data in your C++ program. And then you've got queues, and you can build up command groups. And in those command groups, you tell the SYCL runtime how you're going to access and act upon those buffers. So you say you're going to read this, you're going to write that, you can read-write it. And once you've done that, you can then use those inside Parallel, for example, kernels, which is all inside the same C++ source and code base as the rest of your C++ program. There's some language restrictions inside of kernels. It's very similar to what we talked about earlier, things like virtual functions, etc. are not allowed. So from like a build engineer or a developer's state of mind, the overview of how it builds is again split. Because it uses standard C++ and doesn't have any language extensions, SYCL code goes through any standards compliant C++ compiler, be that GCC, Clang, Intel, or Visual C++. And from that, you'll get your CPU object file and link it into your executable object. And then you can use device compilers, which then run over the source code again to allow the compilation of SPIR or other binary formats. The implementation of SYCL has a linking step, which is implementation defined. but everything ends up in the executable object. So, I mentioned the language extensions. The tasks like actual executing the kernel, mapping copies of buffers, etc. That's all scheduled automatically. And because we bind our data in C++ to buffer objects, and then we tell the runtime how we're going to act on those buffers, the data access rules allow for really efficient scheduling and to reduce overhead, so the runtime can tell when it can use like lazy copies of your buffers, etc., when it knows it can do that. It also allows for hierarchical parallelism. First, just the task graph deduction is very simple. You can have a queue that has 3 different command groups, and you can specify that this buffer here is reading write buffer A, and then the green one is reading and write buffer B. So those can get scheduled at the same time. And then later on, the blue group, which also accesses buffer A, can get scheduled later on. That's all done for you. And you don't need to worry about anything when you're writing your code. Hierarchical data parallelism is a really nice way to write your code to kind of understand the concept of work groups and work items. So we have facilities to, say, parallel for work group, and also parallel for work item. And it makes things performance portable, and you do not need to think about barriers because it can be automatically deduced. And it's easier for developers to get in there and write their code. So for developers, this is really great because you can have a standard C++11 code base and it can target multiple OpenCL devices. It also means that SYCL is cross-toolchain as well as cross-platform, because no language extensions, standard C++ compilers can build the SYCL code. The vendors and device compilers, you can run multiple times on the same source code to build up lots of different support. And it is implementation defined, but it doesn't affect the original source build, so you've always got that there to do things like provide host CPU implementations. So as it's C++, in a header, you can actually implement your CPU device just using standard C++ threads. And it's perfectly okay for you to do that. And that means you've got no external dependencies at all, and allows for developers really easily move over to writing SYCL code. You've got methods there for dealing with targets which don't have OpenCL yet, and you'll get all the synchronization parallelism wins. It's just running on the CPU, multi-threaded on the CPU, but it's really easy to move on and get things running very quickly. And that also means that you can debug all of your SYCL code using standard CPU C++ debuggers. And it also means that profilers work on the CPU device. Now, obviously, you're not going to be debugging on all the different devices, but for developers wanting to dip their toes in, get right into SYCL, this is a fantastic way of doing that. All the existing tools work. And it means the cost of entry into writing SYCL code and using SYCL in your project is very, very low and approaching nil. But you can still get in there and optimize if you need to. SYCL does provide ways of, if you're a seasoned OpenCL programmer, going in there and optimizing the hot parts of the code. So you can access OpenCL objects from SYCL objects, and you can construct SYCL objects from OpenCL objects. So it doesn't stop you from also using OpenCL if you're using a library which uses OpenCL in its own. The interop with OpenGL remains, and if you're familiar with the types there, they're just the exact same. And so developers have the ability to optimize at a low level should they need to. So in summary, SYCL's royalty-free, cross-platform, and its programming layer built in C++. It's single-source development without language extensions, so it allows developers to really use OpenCL very quickly in their source code. Cost of entry, exceedingly low. And the features described today, just a small amount of them, but the task graph, you can express your parallelism very nicely in your code. And host fallback allows you to use CPU debuggers and profilers that already exist. You can fine-tune your code with OpenCL deep down where you need to. So yeah, like I said earlier, the provisional spec is available on the website, and you can use the forum thread for any feedback. It'd be really great to get more feedback on that. There is an implementation called SYCL, which is up in GitHub. AMD have done it, and that's, like I said before, you can write a CPU implementation very easily. That actually uses OpenMP to do parallelism, so you could actually check that out and go try using that if you want. Could play with an implementation in development as well. The next steps we need full specification based on your feedback, conformance test suite, and the release of implementations. So I think that is everything. So thanks very much.
I'm the founder of Khronos, which provides the benchmark for graphics and compute APIs, besides other. And compute bench is our main compute API, and we will release multiple API support versions this year, not just for OpenCL 1.1 and 2.0, but we also support CUDA, Metal, even render script if the language will be still alive. And basically in the new versions, we try to support the new features like artificial neural networks, computer vision, and one of the things we always develop every year is a new ray tracing engine. And this ray tracing engine also runs in real time. Okay. It's getting better. And this ray tracing engine provides new features. And I just wanted to show you this 30 seconds video. So basically we use global illumination in this scene with physically based materials and subsurface scattering, a lot of features. This scene was developed more like a debug scene. It's not a gaming-like scene because we wanted to showcase the current engine versions. But in the final version, we will also have a more dynamic one which can use this kind of new effects. So basically that's it.
So does anyone have any questions? I have a few questions actually that came up through, but I want to open it up to the audience. But whilst you're thinking, so Colin, I think it's actually quite interesting because we've talked about C++ in two different dimensions, and you explained the power of a single source, but it's kind of confusing potentially for people coming across this the first time. Wait, you have a C++ kernel language and you have a SYCL, which is also C++. I mean, okay, perhaps can you give an example of someone who might choose to use the kernel language and who might choose to use SYCL and why? I mean, how do the two relate to each other?
Yeah, well, I mean, SYCL is really great for people who already have a very large body of code or an application, and they might not have the engineering teams available or etc. to kind of change their source, or they might not be able to change their source for whatever reason there, or not a massive amount. And SYCL, in the single source model, allows them to very easily and with a very clear workflow move their code into such a way that it will allow for acceleration with OpenCL. And like I mentioned in the talk, the barriers of them developing in SYCL is very, very low. And at that point, once they've got SYCL up and running, they have the ability then to profile using the CPU profiling tools, etc., and go in and then they can optimize the hot parts of their code with the OpenCL interrupt that we've got there.
Right.
So it's really useful for that sort of situation.
Right. So the current SYCL is running with OpenCL 1.2, correct? So now that makes sense because it's a kind of a pipeline. You know, we have the OpenCL core, and then SYCL can come up after. But eventually, I guess we'll have SYCL for 2.1.
Yeah, I think
so. How would the two C++s, when we get to that stage in the future, how would the two C++s interact?
Well, yes, that's for the feedback of everyone, getting everyone involved in working out standards as they go through all the different steps.
Okay.
As was being said with like SPIR-V, etc., just the ability to build all these different languages on top is just
That's my phone, sorry. Shut up, go with it.
There's massive scope there for what we can do with what SPIR-V provides.
So you're going to use SPIR-V in the SYCL chain in the future?
Well, it's open to us. So, yeah.
Okay. All right. Any questions? So, yeah, go ahead.
I haven't played with OpenCL, got stuck into CUDA again, performance analysis, right? But was there a plan at some point to expose like a special kernel, like as an abstraction of specific fixed function parts on the like hardware? Is that in there somewhere?
Yeah, we do have that. Lee, do you want to talk about custom kernels?
Well, the functionality is there in the API to use custom kernels and to query what's available. Whether any vendor is providing any is a very different question. I think there are some.
Yeah, it's more in the embedded space rather than mobile and desktop, where you have dedicated hardware blocks. Yeah, but custom kernels have been there since 1.2, I think. Yeah. So it's
one question would be, especially because the intermediate representation is seen now in the graphics APIs.
Yep.
Talking specifically about GPUs now, which I'm interested in.
Yep.
It's like, I don't know, I'm always thinking like, how can I abuse the hardware that's not available in the compute APIs to do other tricks, right? Like,
Sure.
Could I write a custom kernel that would be basically whatever's left of the vertex shader, right? Which, to the best of my knowledge right now, does some form of things not on the
yeah, the primary use of custom kernels is if you literally have a hardware block, you can wrap it up so it behaves like a kernel. But that's an interesting question, whether you could use a weird piece of GPU. Could you wrap that up in a custom?
Anybody thought about that?
I don't know. That's an interesting thought.
Well, you probably could, but equally you could use the graphics API and the compute shader. So you might look at that the other way and see whether the compute shader capability that you can get to from the graphics API is enough to satisfy your compute needs. And obviously, we can't go into any detail about what's available in Vulkan yet. I don't know what they're going to say about that tomorrow, but you can come at it from that angle.
Yeah, Vulkan is...
Beyond that, I don't know, really. I suppose
Right.
it would depend on the way different hardware expose those units.
Right. Vulkan, especially with 1.0, is very much focused on GPUs. It's less heterogeneous than OpenCL. They're converging in many ways, but that's at the moment that's kind of the key difference. Is Vulkan is GPU or multiple GPUs. OpenCL is much more heterogeneous, including using multiple cores on the CPU. Yeah, go ahead.
It's like I haven't looked too much into it, but I've heard that the C++ Answer Committee has some working groups looking into how to expose GPU features in a standard way for C++. I was wondering if any of you know if there's any overlap with those ideas and what you're working on.
Good question. Do you want?
No?
So, no, I think, so there's definitely overlap. The approach that the C++ committee is coming from is I think, a long-term view of trying to expose things in a very clean way that's not going to change too much. But some of the stuff they've been looking at, I think, does overlap with SYCL in particular. We have looked at implementing some of the early drafts of the parallel constructs from the C++ standards using SYCL. And it works. So C++ is just a language spec. You'd still need the right tools to implement it and the right way to consume what you generate. And so SYCL as a spec for how to map down from C++ to SPIR and then to the OpenCL runtimes may be a good way to implement the standard libraries that C++ defines for parallelism.
Do you have any comments, Colin? Do you want to?
No, I was just going to, the point about, yeah, is the point that you could use SYCL to implement those runtime functions. It's basically.
We do have members that go to both, so it's not like we are conscious of what's going on. I mean, we would not want to diverge, and we would want to leverage everything. So, but yeah, no, we need kind of what OpenCL gives us at least today to deliver parallelism in a pragmatic way. So Lee, I have a question. The C++ compiler is offline, so which is good for many people. But what if people want to actually do runtime C++?
Yeah, I think saying the C++ compiler is offline is not the right way to look at it. The C++ compiler is not required to be embedded in the driver. Is the right way to look at it. So the spec does not say you as a vendor must have a runtime C++ compiler. But the spec also doesn't say that you as a vendor cannot provide an online C++ compiler.
Right.
And there are people who want online C++ compilation, and it's just that not everyone does. I don't. But there are definitely people who do, and it's a useful thing to provide. And so it is perfectly possible for a vendor to provide a linkable compiler library that consumes the C++ kernel language strings, spits out SPIR-V. And even though one vendor provides that compiler library, it could be an OpenCL vendor. It might not be. It might be Codeplay, who just provide tools. They might provide a runtime library. And then you link it in your application, and it spits out SPIR-V, and it's still portable. And you know exactly what C++ front end you're getting. So you don't have that situation of moving your code and finding that now it's being consumed by a C++ front end that does something different and breaks. You know exactly what you're getting. But the portability is then defined at the SPIR layer. So yes, I'm sure it will be available.
It's going to be available. Okay. Any other questions? So I have a question for you, Ron, because you live in compiler land, right? And you remarkably come through it unscathed. Do you have any thoughts as to what languages will take advantage of SPIR-V? We're kind of crystal ball gazing, but from your engagement in the compiler chains, where do you see interest in higher level languages and frameworks in using SPIR-V?
We were kind of joking among ourselves about this earlier, but we have seen people ask, I don't know how seriously, but for Fortran. I've seen somebody ask for can we build Haskell on this thing? I think this is one of the powerful things about SPIR-V is you don't have to wait for us guys or Khronos to specify a language anymore. Hopefully SPIR-V gives you the opportunity, or somebody the opportunity to build whatever language they want. And if it ends up being Fortran or Haskell or none of the above, I mean, that's great from us. It just means more people using OpenCL. And that's really the goal behind SPIR-V.